Hi, I'm Colin. In this module, we're going to use polynomial long division to help us solve the cubic polynomial equation x cubed plus 3x squared plus 4x plus 12 equals 0. Recall long division with numbers from your earlier schooling days. For example, if we divide the number 13 by 3, then we get 4. Because 3 goes into 13 exactly 4 times. But we also have something left over, the remainder, which in this case is 1. The number that we start with is called the dividend. The number we're dividing by is called the divisor. This then gives us the quotient. Along with the remainder. Now, what are the consequences of this long division? Well, what this procedure really allows us to say is that the number 13 can be decomposed into 3 times 4 plus our remainder 1. In other words, the dividend can be written as the divisor times the quotient plus whatever the remainder is. Alright, if we divide 12 by 3 now, we get the quotient 4 once again. But this time with remainder 0. Thus we can say 12 can be decomposed into 3 times 4 plus a remainder of 0, which we can leave out. There is an important observation to be made here. This expression is a factorization of 12. That is, 12 can be written as the product of the factors 3 and 4. So an important idea to drill into one's head is the notion that when you're dividing by something and there's no remainder, you have actually obtained a factorization for your original dividend. Now let's look at the same idea, but with polynomials rather than numbers. The technique of polynomial long division can be used to divide a polynomial of any degree by a polynomial of a lesser degree. Specifically, we're going to divide the cubic polynomial x cubed plus 3x squared plus 4x plus 12 by the linear polynomial x plus 3. Show that we get the following quadratic quotient and a remainder of 0, thereby giving us a factorization for the original polynomial. Thus, the technique of polynomial long division plays an integral part in the factorization of general polynomials. We're then going to use this factorization to help us solve the original polynomial equation. A very important question is, how did we know that dividing by x plus 3 would give us the 0 remainder that we sought? Well, recall the piece of theory from class that asserts the following. If we call the original polynomial function p of x then whenever we can guess a number which when evaluated gives 0, then x minus that number must be a linear factor. Alright, so that's the plan. Let's now go back a bit and fill in the details, starting with a polynomial long division algorithm. The first step is to grab the leading term of the dividend and divide by the leading term in the divisor. This gives us x squared. The x squared then gets a term multiplying every term in the divisor, and we write the results in the next line under the original polynomial. So x squared times x is x cubed. Observe that in the procedure, these two terms should be the same. And x squared times 3 is 3x squared. The next step is to subtract the terms. X cubed minus x cubed, that goes away. And 3x squared minus 3x squared, that coincidentally goes away as well. The terms that we haven't interacted with just yet, you bring them down. Or you could think of it this way. 4x minus 0x is 4x. 12 minus 0 is 12. We now iterate the above procedure again in another cycle. So leading term divided by leading term is going to be 4. And this 4 is going to have a term multiplying everything in the divisor. So 4 times x is going to be 4x. And 4 times 3 is going to be 12. And now we subtract the terms. 4x minus 4x is nothing. And 12 minus 12 is also 0. We now terminate the procedure because the degree of this polynomial is less than the degree of the polynomial of the divisor. That's because any constant can be regarded as a degree 0 polynomial, while the degree of any linear polynomial is always 1. And so in conclusion, the remainder here is 0. And so we obtain the factorization x cubed plus 3x squared plus 4x plus 12 is equal to x plus 3 times x squared plus 4. Now this means that solving the original cubic polynomial equation is the same as solving the following equation. Where we've now factorized the cubic polynomial, where this factorized form can take advantage of the null factor law from number theory. Which says that if a bunch of things multiply together give 0, then at least one of these factors must be 0. So here we can set each of these factors to be 0, thus giving us a separate pair of smaller equations to solve. For the linear factor x plus 3 equals 0, x is therefore negative 3. So that's one solution to our equation. For the quadratic factor x squared plus 4 equals 0, this gives x is equal to plus minus the square root of negative 4, which isn't actually a real number because you can't square root a negative number. Thus, this second equation gives us no real solutions. You can also reason this by looking at the equation here. Notice that something squared is always positive, or at the very least 0. And if you're then adding 4 to that, you're getting something even more positive, which in any case will certainly be bigger than 0. Thus our set of solutions is the set comprising just one element, the integer negative 3. This set is an example of what's called a singleton, because it only has a single element inside. Generally speaking, an n-degree polynomial equation has at most n real solutions. Here, our cubic polynomial could theoretically have a maximum number of 3 distinct solutions, but it turns out that there was only one. For us to have obtained 3 different solutions, we would have needed the quadratic equation here to give us another 2 solutions, but instead it gave us none. Also, a final comment on terminology. Solving this original polynomial equation is also known as finding the roots. Or zeros of the cubic polynomial regarded as a function. In general, when one says to find the roots of a polynomial, that means you're solving the equation obtained by setting that polynomial to be 0. Alright, I hope you found that useful. See you next time.